Hi, in this video I'm going to introduce to you all the concept of nuclear magnetic resonance. I've designed this module especially for the undergraduate students of Mumbai University, and it is advised that they go through this module before they start going through the books to understand what NMR is all about. Now I'm sure all the undergraduate students in chemistry know that nuclear magnetic resonance is a spectroscopic technique. Now first of all, what is spectroscopy? So spectroscopy, I'm sure all of you all know, is the study of interaction between light and matter. So between electromagnetic radiations and matter. So when I said light out here, I meant electromagnetic radiations such as visible light, UV light, infrared light, radio waves and microwaves. Now the type of spectroscopy involved depends on the frequency or the wavelength of the electromagnetic radiation involved in interaction with the matter. And the type of interaction involved in NMR is the interaction between the nucleus and electromagnetic radiations which belong to the radio wave region. The next question arises is, why should we learn NMR? Why is it so important in chemistry? The most important use of NMR in chemistry is the structural elucidation. So NMR helps us to determine the structure of several organic molecules, and hence it is a very important technique in research in pharmaceutical industry and in organic chemistry. Apart from that, NMR can help us to understand the reaction kinetics and study of equilibria. A type of NMR called a two-dimensional NMR is used for structural studies of proteins, DNA and RNA, and also of polysaccharides. So the spectroscopy finds a huge amount or large amount of application in biological sciences, and apart from that it is also useful in drug design, and also magnetic resonance imaging, which is popularly known as MRI, is also an offshoot of NMR. As I just told you all, any kind of spectroscopy involves interaction between electromagnetic radiations and matter. So what is the interaction involved in NMR? So the interaction involved in NMR is that between a spinning nucleus and radio waves, and this interaction comes about only when the nucleus is placed in a magnetic field. So basically in this spectroscopy, a spinning nucleus absorbs radio waves and undergoes a transition from one energy level to another. Now as we just learned that NMR is interaction between nuclei and electromagnetic radiation, so the next question that arises is that, do all nuclei show NMR? You'll be a little disappointed with the answer that all nuclei cannot show NMR. Only those nuclei which have spin number which is non-zero can show NMR. So nuclei with spin number which is non-zero can absorb or emit radio waves and show NMR spectroscopy. Now if an element has atomic number and mass number which is both even, for example carbon 12, its atomic number 6 is even and mass number 12 is also even. So it has even number of protons and also even number of neutrons, which is 12 minus 6. In such a case, the spin quantum number of the nucleus is 0 and it cannot show NMR. Another example being oxygen 16, that is atomic number being 8 and mass number being 16. There are even number of protons which is 8 and the number of neutrons are 16 minus 8 which is equal to 8 and hence even. So therefore oxygen 16 is not capable of showing NMR spectrum. However, if a nucleus has either odd atomic number or mass number, or both odd atomic as well as mass number, then it is capable of showing an NMR. For example, if atomic mass number is even but the atomic number is odd, in that case the nucleus will have both the number of protons as well as number of neutrons as odd. For example, in nitrogen 14, the atomic number is 7, mass number is 14. As a consequence, there are 7 protons and the number of neutrons are 14 minus 7, which is equal to 7. And as a consequence, since number of protons and neutrons are odd, this particular nucleus has an integral spin. So the spin quantum number is an integer or a whole number. Another example would be deuteron. Deuteron is an isotope of hydrogen, as you all know, with atomic number 1 and mass number 2. So it has odd number of protons, which is 1, and number of neutrons is 2 minus 1, which is 1, that is also odd. So as a consequence, deuteron has an integral spin. Now those nuclei with odd atomic mass number have half integral spins. Now what do I mean by odd atomic mass numbers? If they have odd atomic mass numbers, it is quite likely that either they will have odd number of protons or odd number of neutrons. For example, protium, which is H11, has 1 proton and 0 neutrons. As a consequence, it has odd number of protons, and if we consider 0 as even number of neutrons. Similarly, carbon 13 has even number of protons, but the number of neutrons will be 13 minus 6, which is 7, which is odd. So as a consequence, as the atomic number is odd, we can say that carbon 13 has a half integral spin. Similarly, nitrogen 15 will be having odd number of protons, which is 7, and even number of neutrons, which is 15 minus 7 equal to 8. So basically, if a nucleus has either odd number of protons or odd number of neutrons, or both are odd, in that case the nucleus is capable of showing NMR spectroscopy. Whereas if a nucleus has even number of protons as well as neutrons, it will have 0 spin and it will not be capable of showing NMR spectroscopy. It will not be capable of showing NMR spectrum. Now, from our syllabus point of view, what type of nuclei are we interested in? So if we limit ourselves only to the syllabus, then we are interested in hydrogen nuclei, that is protium, which has odd number of protons, which is 1, and 0 neutrons, which is even, and as a consequence has a half integral spin. So the spin quantum number for protium is half. So we are interested technically in a type of NMR called PNMR or PMR, which stands for proton nuclear magnetic resonance. Now, if a proton, that is a hydrogen nucleus, is placed in a magnetic field, it has 2 spin states. The lower one is called the alignment orientation, and the higher one is called the non-alignment orientation. So let's see the diagram for that. This is the energy of a hydrogen nucleus when it is not in the presence of a magnetic field. So when there is no magnetic field, the energy of a protium is this much. However, if a protium is kept in a magnetic field, it will assume either of these 2 energy levels. This is called the alignment orientation, which is a low energy state. And in this state, the nucleus will spin in such a way so as to support the applied magnetic field. However, in this particular orientation, which is called the non-alignment orientation, the high energy orientation, the nucleus will spin in such a way in the magnetic field that it will oppose the applied magnetic field, and hence this is a high energy state. So I'll repeat, a hydrogen nucleus when not placed in a magnetic field has only one energy state. However, once it is placed in a magnetic field, it has two energy states available, one with lower energy where it spins in such a way the magnetic field which the proton generates is in the same direction as the applied magnetic field, whereas the higher energy orientation is called the non-alignment orientation. The proton spins in such a way that its own magnetic field opposes the applied magnetic field. So the alignment orientation, which is a low energy orientation, is assigned a spin of plus half, and in the high energy orientation the spin assigned is minus half. Now, what is the difference between the two energy levels which we are talking about in the previous slide? The energy difference is dependent on the applied magnetic field. The stronger the applied magnetic field, the greater is the gap between the two levels, which is the alignment level and the non-alignment level. So the energy difference between the two levels is directly proportional to the applied magnetic field. So that means the greater the applied magnetic field, the greater is the energy gap between the two orientations, which is the alignment orientation and the anti-alignment or non-alignment orientation. Now the energy gap between any of these two levels is corresponding to the energy of radiations in the radio wave region, and hence radio waves are quite capable of transferring these protons from the lower energy level to the higher energy level. So basically, to bring about the transition, it is the radio waves which are required in NMR spectroscopy. This graph is clearly depicting that the energy gap between the two levels increases with the applied magnetic field. So the energy is on the y-axis and the applied magnetic field is on the x-axis, and as the applied magnetic field increases, the energy gap between the two levels increases. Now, what is the relative proportion of the hydrogen nuclei in the two energy levels? Now, if the energy gap between the two levels is delta E, then according to Boltzmann distribution equation out here, it is found that the ratio of number of atoms in the alignment orientation as compared to that in the non-alignment orientation is slightly more than 1. So I'll repeat, the ratio of number of hydrogen nuclei in the alignment orientation as compared to that in the non-alignment orientation is slightly more than 1. This indicates that there is a small excess of nuclei in the lower energy level as compared to higher energy level, and as a consequence it makes the study of NMR possible. This is because if the two energy levels, the alignment and the non-alignment orientations, had equal amount of energy, in that case there would be no net absorption of radio waves, and as a consequence NMR spectroscopy wouldn't have been possible. Now, how is the NMR spectrum obtained? That means, what is the technique used for obtaining NMR spectrum? So there are two basic methods. One method involves bombardment of radio waves of different frequencies on the sample, keeping the strength of the magnetic field constant. And the second one involves bombarding the sample with a radio wave of constant frequency but varying the magnetic field strength around the sample. Now, the second method is highly preferred as it is very difficult to maintain magnetic field strength at constant value. Now, what would an NMR instrument consist of? So, any instrumentation in NMR should involve a magnet, as we need to place the sample in a magnetic field, and we need a frequency generator to produce radio waves, a detector to detect those radio waves, and a recorder to obviously record the data. This is a schematic diagram of an NMR instrument. So this is a transmitter which generates the radio waves. This is a receiver which receives the radio waves. The magnetic field is created between the two magnets out here, and the sample is placed in a tube out here. The sample is dissolved in a non-protonated solvent, maybe like deuterated chloroform, and the sample tube is made to spin at a constant rate. This is how the NMR instrument looks like externally. The next question that we face is, do all hydrogen nuclei in a sample or in a given molecule absorb radio waves at the same magnetic value. So as I told you all, we keep varying the magnetic field and bombard the molecule with a constant frequency radio wave. So the answer is a big no, but how? So basically, hydrogen nuclei absorb radiations depending on their chemical environment. Different hydrogen nuclei having different chemical environments absorb radio waves at different magnetic fields. In such a case, we say that chemically different hydrogen nuclei have different chemical shift. So the term used is chemical shift. So I'll give you an example, say an ethanol molecule. Now ethanol has three different types of hydrogen atoms. The hydrogens which are present in the methyl group, then the hydrogen which are present in the methylene group out here, and the hydrogen which is directly attached to the oxygen of the hydroxyl group. Now these three hydrogens are considered to be chemically non-equivalent, and they will have different chemical shifts. Whereas the hydrogens belonging to the same atom, like for example all the hydrogens of methyl group are equivalent and they will have the same chemical shift. When an ethanol molecule is placed in a magnetic field, the three different types of hydrogens do not feel the same magnetic field. That means the effective magnetic field experienced by each of these hydrogen atoms is different. If B0 is the applied magnetic field and LOC standing for local, so B local is the magnetic field created by the electrons around the hydrogen, then the effective magnetic field experienced by a hydrogen atom or nucleus will be B0 minus B local. Now this local magnetic field created by the electrons around the hydrogen nucleus is directly proportional to the applied magnetic field, and hence I can always write B local as some constant of proportionality K into the applied magnetic field. This constant of proportionality is called the shielding constant, and the symbol for this shielding constant is sigma. So we can write the local magnetic field created by the electrons as sigma into B0, where sigma is the shielding constant. So if I substitute this in the formula, we'll get B0 into 1 minus sigma. Now this shielding constant for different nuclei is different, and therefore this effective magnetic field as experienced by different nuclei will be different. Have a look at the spectrum of ethanol. As I told you all earlier, there are three chemically non-equivalent protons, the ones belonging to methyl group, the second group belonging to methylene group, which is the CH2 group, and the third one belonging to the OH group. Now it so happens that this hydrogen, which is attached directly to the oxygen out here, experiences the highest effective magnetic field. As in this OH group, the oxygen is directly attached to hydrogen, the electrons are withdrawn more towards oxygen as it is highly electronegative. So as a consequence, the electrons of the bond between oxygen and hydrogen are quite far away from the hydrogen nucleus. As a consequence, the magnetic field experienced by a proton is going to be far larger as compared to the other protons in ethanol. So as a consequence, to show NMR spectrum, the OH group will show a peak at a very low magnetic field, and in such a case we say that the OH group is de-shielded. Whereas if we look at the hydrogens belonging to the methyl group, the electrons are quite close to hydrogen. As a consequence, the protons of methyl group experience a small effective magnetic field as these electrons are very close to the hydrogen nuclei and apply a magnetic field which opposes the applied magnetic field. So as a consequence, the methyl peak is obtained at a very high magnetic field, and hence the tallest one out here is the methyl peak. Obviously the methylene peak is going to be in between. So depending on their electronic environment, we have got three different peaks for three chemically non-equivalent protons or hydrogen nuclei. Now the area under each of these graphs is directly proportional to the number of hydrogen atoms present. So the area ratio under each of these peaks will be 1:2:3. Now to basically understand the concept of chemical shift, you will have to look at this diagram. This is the applied magnetic field. Now when an electron is placed in a magnetic field, it's going to spin in such a way that it's going to oppose the applied magnetic field. And hence, if a hydrogen nucleus is quite close to an electron, then this electron applies a magnetic field which opposes the applied magnetic field, and as a consequence reduces the effective magnetic field acting on a nucleus. So basically, whenever an electron is kept in a magnetic field, it rotates and generates its own magnetic field, and this magnetic field opposes the applied magnetic field. So as a consequence, if an electron is very close to a proton, then the opposition to the applied magnetic field is going to be quite large, and hence as a consequence the effective magnetic field on the nucleus will be very small. As a consequence, that particular proton will show a peak at high magnetic fields, and such nuclei are said to be shielded. However, for protons which are attached to highly electronegative atoms, for example the H in any OH group of an alcohol molecule, electrons of the bond are quite far away from the proton, and therefore the effective magnetic field experienced by a nucleus like this will be large, and if it is large, the proton will show an NMR spectrum at a very low magnetic field, and in that case we call such protons to be de-shielded. This explains clearly why the NMR spectrum of ethanol has three different peaks, and not only that, and it also explains why the proton of the OH group shows a peak at very low magnetic fields, whereas the protons of the CH3 group show a peak at high magnetic fields.